In this lecture, let us discuss FIR filters. FIR stands for Finite Impulse Response. As you know, FIR filters is of the form h of z is equal to summation h of k z to the minus k equal to 0 to capital N. And here this capital N denotes length or sometimes order. So here I will use filter order. Sometimes I may use capital N to denote the length of the filter also. So beware of the terminology. So you have to keep track of what it stands for. Here obviously if N stands for filter order, then N plus 1 is the length of the filter. And this is very straightforward, and you can see that y of n is equal to summation h of k x of n minus k equal to 0 to capital N, order of the filter. So if I derive a structure which uses these coefficients, and incidentally, as I have always done, in order not to write these brackets again and again, like h of k, instead of writing h of k again and again, let me use a subscripted form, subscripted h, that is h suffix k, to show this or this as the function of k. Now for a general structure you can write it. Let us do it for a specific example. This is a general form, right? General structure. Let us do it for a specific structure or specific example. Let's say capital N equal to 4. I mean it's a fourth order structure. Fourth order filter, or I can say structure, digital filter structure. Okay. Then my transfer function, a capital H of z, is equal to summation h of k and z to the minus k equal to 0 to 4. So in order to realize this, a very simple minded realization is, first you draw all the 4 delays. See, I have 4 delays here. Okay, so k equal to 1, 2, 3, 4. So let me draw the delays. So the input is here, x of z. So the input is multiplied by, let me draw the delays first, z inverse, and then z inverse, z inverse, z inverse. So there are 4 delays, right? The input is here in this point, and so the input is multiplied by h0. Then after one delay, the input is multiplied by h1, and the 2 signals are getting added like this. Then after 2 delays, the input is multiplied by h2, and this adds the result of this guy. And therefore we will have another summer here. Similarly, we have another multiplier h3, and this one adds with the output of h3 like this. And finally you have h4 and these two are getting added here, and this is your output capital Y of Z. And this is the pickup point. So don't forget to put the arrow mark. And this structure is called direct structure, because the multipliers are obtained directly from the transfer function. See, the transfer function is h of 0 plus z to the minus 0, that is 1, plus h of 1 z to the minus 1, plus h of 2 z to the minus 2, plus h of 3 z to the minus 3, plus h of 4 z to the minus 4. Now if you look at the multipliers, h0 the same here, and h1, and here also h1 same, h2 h2, h3 h3, h4 h4. So there is no change in the coefficients which is given in the example. So whatever the coefficients are given, or whatever the coefficients are present in the transfer function, that same coefficient is used in the structure. Therefore this is called a direct structure. Okay, so this is called a direct structure because the multipliers h0, h1, h2, h3, h4 are obtained directly from the transfer function. Okay, we did not do any manipulation on the multipliers. Okay, so therefore in direct structure no manipulation is needed. No manipulation is needed. Now if we make a transpose of this and then flipping over, then obviously what you should get is the following. So let me draw it. Just transpose this. As I said, first you replace, interchange the input and output. So this point is output, and the pickup node becomes a summer. You put a summer here. So this is Y of Z, summer, then delay, then again another summer, then delay, another summer, delay, then summer, delay. Okay, then here H0, and I'm sorry, this has to come from here, H0, and then here H1, and this should be a pickup point. I'm sorry, this goes like this, and then H3, pickup node, H0, H1, this is H2, H3, and then H4, like this, and this point is X of Z. Reverse the arrow mark. So it goes like this, and then comes like this, like this. So this is a transposed structure, but I need to keep the input on the left hand side and the output on the right hand side. Just to flip over the diagram. So X of Z, then maybe I'll X of Z, you draw a straight line, H4 is given to z to the minus 1, then a summer z to the minus 1 z inverse, then a summer z inverse, okay. I have x of z here. Now I write the coefficients in the reverse order, right? So that is h4 should undergo 4 delays. So first x of z is multiplied by h4 and undergoes 4 delays. 1, 2, 3, 4, you put one more delay, z inverse. So let's draw the delays, and h3 is multiplied by x of z should undergo 3 delays, therefore you put h3 here. Now h3 goes 3 delays. Look at in this figure, in the above figure, h3 goes 1 delay, 2 delay and 3 delay, therefore here also 1, 2, 3 delays. You see the pickup points are now being replaced by summers, and h2 will be multiplied by z to the minus 2, therefore it comes here. So 2 more delays are needed here, 1 and 2, fine. And this summer I have only one delay, let's say h1, and you put one more summer here, and this is h0. h0 no delay, if you look at here, see, no delay for h0, and this is your y of z. X of z is here and y of z is there. Don't forget to put the arrow mark. So this is the transposed structure of given FIR filter. Therefore the output of this summary is capital Y of z. So this is obtained by transposition of this structure. Okay, and this structure, the given structure and the transposed structure are a valid structures. Okay, they are valid structures in their own right, but in practical implementation the properties are different. As I said, word length effect and the word length effect, and one more property which I said. Okay, so these two properties are different. Truncation error. So these two things we need to remember. One has to be very, very careful about these things. And overflow. And this word length effect comes because of this truncation error, and there is a overflow because of the hardware limitations. And this structure also known as transversal structure. And earlier authors and current authors also call one of them as direct form 1 structure, and this is direct form 2 structure. These nomenclatures are not important for us, as long as you can obtain this structure and equivalent structure. what is 1 and what is 2 is not important. Okay, so what is direct form 1 and what is direct form 2 is not important. The transversal structure requires n multipliers, n minus 1 adders and n minus 1 delay elements. N minus 1 delay elements, n minus 1 adders and n multipliers. These are the hardware requirement. Now let us take an example. And there are indirect structures also for FIR filters. For example, if h of z is an odd order transfer function, then I can factorize the h of z into one first order and a number of second order factors. For example, if the order is 5, then you can factorize into one first order factors and 2 second order factors. One first order factor. Therefore, in this case, let me write down h of z summation. 1 minute. I lost the paper. So h of k c to the minus k, this is the transfer function. Now what you do is you factorize this. Okay, so you have to take h0 commonly outside. Then I can write h of z as one first order factor, that is you take h0, then 1 plus beta 0 z inverse and then a number of second order factors, 1 plus beta 1 k z inverse plus beta 2 k z to the minus 2, k equal to 0, no, it's not 0, it is 1, k equal to 1 to n minus 1 divided by 2. Okay, and here capital N is odd, the order is odd. Do you understand why I brought 1 here and here also 1? I have taken h0 out, so I can see the zeros very clearly from the factors. If you write this, then you can write down the zeros very clearly. What is a 0? 1 plus beta z inverse equal to 0. Therefore z, you can write down the values. Okay, z inverse beta is equal to minus 1 and then beta is equal to minus 1 by z inverse and then z is equal to minus beta. Okay, and k going from 1 to n minus 1 by 2, k equal to 1, 2, 3, and how many such factors? N minus 1 by 2 factors. If it is a fifth order, then I will have one first order factor and 2 second order factors. Okay, therefore n minus 1 by 2. Now you can ask a question. Instead of writing one first order factor and 2 second order factors, why can't I write this as a product of only first order factors? Right, 1 plus beta 0 z inverse and 1 plus beta 1 z inverse, 1 plus beta 2 z inverse, like this. Why can't I write in terms of Or why can't I write this as a product of only first order factors? Why not? I could do that, but what would be the disadvantage in writing in this format? Disadvantage, when you try to do in terms of product of first order factors, then you will get complex coefficients. Okay, so if I write the product of first orders, because it is not guaranteed that all the zeros are real or all the factors are real. When you do the factorization, there is no guarantee that you will get all the coefficients are real, right? So if all zeros are real, yes, go ahead, write product of all first order factors. So this is real, and this is real, no problem, go ahead, you can do that. But in many cases it is not so, right? But once you get the complex factors, I mean complex zeros, and then these complex zeros must be written together so that the coefficients are real, because you want to implement the filter in real time with real coefficients, right? Digital filters you need real coefficients for real filters. So we don't want complex number as a multiplier. So because of that reason only, we have taken one first order and number of second order factors. But in the second order factors, you will get a real number, no issues. But there are certain cases where you will get the first order factors and the zeros are all real. In that case, go ahead, you can write in terms of first order factors and realize it, no problem at all. Therefore h of z is equal to h naught 1 plus beta naught z inverse continued product of 1 plus beta 1 k z inverse plus beta 2 k z to the minus 2 k equal to 1 to how many factors? N minus 1 by 2 factors. And each of these factors can now be realized in the direct form, either direct form or its transpose form, whatever form you like it. And then you have to cascade them together because they are in the multiplication. So a cascade, C-A-S-C-A-D-E, cascade, okay, don't confuse with cascode. Cascade means one after another, so you can use it, cascade realization. Now this is for odd. On the other hand, if n is even, then you will not have this first order factor, you don't have the first order factor. Then all that you have is h of z is equal to continued product of 1 plus beta 1 k z inverse plus beta 2 k z to the minus 2 k equal to 1 to now n by 2 exactly, because n is an even number. Now each of them has to be realized in the transverse form or whatever structure you would like to choose. And obviously in implementation I told you, if there exists one synthesis solution, then there are indefinite number of solutions. In implementation of cascade, when you write h of z as equal to continued product of h I of z, where I equal to 1 to capital N by 2, where h I of z is no more complicated than a quadratic. It is either a linear term or a quadratic term. So this hi of z, either it will be 1 plus beta 0 z inverse, or it will be 1 plus beta 1k z inverse plus beta 2k z to the minus 2. Now I have number of this hi of z in the multiplication, okay, one after another. Therefore I can put h1 of z, then h2 of z, then dot dot dot, then hi of z. Not hi of z, n by 2 of z if it is even. And then there is no rule you should follow in this order, okay, first h1 of z, then h2, then h3, like that. Whichever way you like it, you can put it. First you can put h2 of z, and then h1 of z, and then h4 of z, as you like it. Okay, so you can interchange in cascading. The order of cascading is not important as far as the total transfer function is concerned, because they are multiplications, right? So we know that the multiplication is commutative, right? h1 of z times h2 of z is the same as h2 of z times h1 of z. Whatever the order you like it, you put it. But as far as the total function is concerned, there is no change. So multiplication is commutative in theory. So commutative in theory, but if you take in practice, the order of cascading is very, very important. So order of cascading is very important. Okay, very important from the point of view of overflow and word length effect. One order may give certain amount of overflow and a certain amount of word length effect, and if you change the order, then it gives some other amount of overflow and word length effect. Therefore you just try before you implement it. Therefore your job after finding a cascade realization is not complete. Okay, so if you want to implement it, then you must study the quantization behavior and the overflow behavior of the structure. One structure may give you better overflow and better word length effect. And normally what one does is the section with the lowest gain, you put the lowest gain first. Let's say h2 of z has lowest gain. First put h2 of z, and then at the end you put a highest gain. Let's say h3 of z has highest gain, and in between you put h1 of z, like this. So generally don't put the highest gain in the beginning itself. Agreed? So that its output does not saturate. If you put a highest gain in the beginning itself, then the output of then the output of the first block will saturate the second stage. Therefore always what you do is you put the factor which has the lowest gain. Okay, now it may not be possible to avoid overflow, particularly in fixed point arithmetic. Okay, whenever you have fixed point arithmetic, then this overflow is an unavoidable problem. The dynamic range of fixed point arithmetic is severely limited as compared to floating point. So if the overflow happens, if you are keen on fixed point, your all other peripheral structures or all other structures are fixed point implementation, then you cannot suddenly switch to floating point, because already you designed with the fixed point arithmetic. All of a sudden you cannot go to floating point, and if you do that, then that is a costly proposition. So then one may have to scale. In case, let's say if the gain is, let's say some 100 times, then divide by 100. Okay, scale it. So what you do is, since it is a costly proposition to go from fixed point arithmetic to floating point arithmetic, in this case what you do, the low cost proposition is scaling. So if you have, let's say 100, then divide by 100, that's it. Okay, so one may have to scale it. In other words, suppose at the ith stage the signal that you get has exceeded the dynamic range of your storage of the accumulators, then at I minus 1th stage you use the scaling, like by 100 or by 10, like that. So scaling constant is usually not by 1 by 100 or 1 by 10. Generally they will put 1 by 2 or 1 by 4 or 1 by 8, like this. So they will not go in this form. They will choose 1 by 2 or 1 by 4 or 1 by 8. In general they say 1 by 2 power k. So scaling constant is usually of the form 1 divided by 2 power k. So you can divide by 1 by 2. This 1 by 2 is not a multiplier, only a shift. For example, see 1 0 0. What is this? In binary, this is equal to 8 in the decimal. Now if I want to divide by 2, then this is 4 and 8 by 2 is 4. Now this 4, how will you obtain from here? Just shift it, okay, shift to the left. So this 0 comes here. So 0 1, this 1 goes to the next position, and this 0 comes here, and this 0 goes over there. So 0 0, like this. Now what is this? This is 4. Therefore dividing by 2 or by 4 or by 8 is nothing but it is shifting the bits in the appropriate direction. And whenever the dynamic range is exceeded, then you scale it, and the overall transfer function is realized. Not the original transfer function, but you realize it to within a multiplying constant. So scaling is also an important consideration. You may have to do it, and one might ask, why not do the scaling at the input itself? Okay, so you can do the scaling at the output or at the input itself. Okay, you can do the scaling at the output, that is permissible, that is allowed. Okay, you may do it, but at the input, if you do the scaling, then what is going to happen? Your signal is already weak, right? So if you again do by scaling 1 by 2 or 1 by 4, then the signal is prone to another disaster effect. Prone to disaster effect if you do the scaling in the input itself, because in the input the signal is already weak, and if you scale it, then again it will be very weak. Okay, if it is weak, then what is going to happen? Noise will take over the signal. Okay, if the signal becomes very weak, then the noise may take over, and noise corruption occurs. And therefore your scaling has also to be done in a distributed manner, judiciously. Okay, don't do it at a particular place. Instead of doing 1 by 8 at one particular place, if you have a number of blocks like this, there are many blocks, you put 1 by 2 here, 1 by 2 here, like in a distributed manner judiciously, so that you maintain a balance between overflow as well as signal strength, and also the word length effects, that is the quantization error. Okay, that's how one will do the implementation. Okay, so that's it. So let me stop here. In the next lecture, we will discuss the parallel form implementation of FIR filters. Okay, thank you very much.